Okay, when we last left off, we had written a program that was fairly extensible. We could add new functions in to be integrated. We could change the number of iterations, the number of guesses, and this is a good thing. So now it's time to make sure that we have unit tests put in to make sure that everything is verifiable and works as we expect. So again, we can run our program. Let's go 16 iterations, 3,200 guesses. We can integrate e to the minus x, and we can compare it to the exact value, 0.63288 compared to 0.63212. Fine. This is good. This works. But now we have to add tests in. So fortunately, unit testing is built into Xcode, and we have this integration thread test Swift. Now, one of the biggest problems that one has to deal with is unit testing threaded code. You can't predict when something will be executed. You can't predict when something will be completed. Because of that, it's tricky to actually write unit tests for code of this type. And so we're going to discuss some of the tricks that you can use in order to do this. And it turns out we're going to have to make some modifications to our code in order to get this to work. All right, for unit testing, one of the first things we have to do, because we're actually utilizing the view controller for a lot of the work, and some of this code's within the view controller, is we have to make sure that the unit tests understand where the view controller is. So we're going to start by having a variable, myViewController, and it has to be of type viewController. And then in the setup for the integration, we have to add in here instantiation of the view controller. So to do that, we have to utilize the storyboard. So we have to have storyboard equals, and then a storyboard the name of the storyboard will be main, because over here our storyboard is main. And you have to call it with bundle equals nil. All right. Now, the next step we have to do is let myViewController know which view controller. So it's going to be storyboard.instantiate controller. And we're going to instantiate the controller with identifier. And the identifier in this case, I'm going to call JTViewController. And just to be really certain, we're going to typecast this as a view controller. So the next thing I want to do is just make sure that my view controller actually has a view. And so we'll just get it and throw it away. So it'll give us an error if it doesn't exist. All right, this is good, except there's a major problem in here. we haven't set the identifier yet of my view controller. So we have to go and make sure you set the storyboard ID for the view controller to be JT view controller. All right, so if I go to storyboard, I want to click on the view controller. Yeah, I just got to make sure you click on the right thing. All right. Yes, it's not the top one. Sometimes it helps if you're in the view controller scene, click on the view controller, or you can click on this thing. You have identity, the storyboard ID here. I have to set that to JT view controller. All right, so that now has a name. If I click back on it, JT view controller. Now I can come back in here to the threaded tests. All right. Now, I'm going to add another function or another test because I found that it's very easy to make a mistake and you can end up spending a lot of time debugging things when there isn't a problem, that the only problem was that your view controller wasn't created. So I'm going to create a new function, test view controller was created. And so that I'm going to put in a very simple xct assert, and we're going to assert nil, or no, we want to assert not nil. There we go. And my view controller. So this test will be passed as long as the view controller gets created, so we can actually test this right now. And it found my view controller because we actually gave it the identifier, passes the test. So now we can be pretty sure that as we go forward, any errors that we have are not because of the lack of the view controller being present. Okay, so the next step then is to go into the example. And we'll write this test integration of e to the minus x. Okay. All right. So we can set up test value was 3.14159. That's an incorrect value. Now we have to be very careful and creative with what we're actually going to attempt to do. So this becomes a little bit problematic. Because we have to worry about how the system is going to interact. When will it be finished? When won't it be finished? How do I make sure that I have a new value for test value before I actually run my assert as equal? And so that becomes the problem. I have to make sure that I have my calculation completed, and I don't know when my calculation is going to complete. So to do this, I'm going to run this in its own queue. So I'm going to say let my queue equals dispatch queue. And I'm going to label this queue as e to the minus x test. So now I'm going to set the values that I need to set to get the calculation to run. So I have to set dimensions equal to 1.0. I need to set my view controller dot exact equals, in this case, negative exp negative 1.0 plus exp of 1.0. And I have to set the integration function. My view controller dot function for integration equals e to the minus x. Fine. All right. Now I should fix that because I spelled that wrong. All right, there we go. So now I've set those values. Okay. Now we would think I would need to set as well the number of iterations and the number of guesses. But it's not easy to run this using the interactive method. So I'm just going to call the integration function directly. Now to do that, I'm going to go myQueue.sync. And this is going to run a synchronous calculation in the queue that we created called myQueue, that we've labeled e to the minus x test. So we're going to go my view controller dot integration, and we're going to pass in the number of iterations. So we'll go 16, 3200, but we now have to do something else. We have to give it the queue to run in, and we want it to run in the queue that we just created called myQueue. Now the problem is the integration term doesn't have a parameter myQueue or the queue. So it's telling me there's an extra argument in the call, and we'll have to add that in to make this work. Okay. Then when this was done, we want to call in the same myQueue, again synchronously. We want to now determine what the value of the integral actually is. So here we want to get self.myViewController.integral. That's the value held within the function itself. All right, so we have the function that's in the function. We know what the right value is, so we just want to check these now. So now we run our XTC or XCT assert equal, and we want to have test value because we want to check that, the returned integral. against the exact value. So self.myViewController.exact. Then if it's not the case, we need an accuracy here too, because these are, so we have accuracy 1.5. So we're not running this to be the world's longest calculation, so 1.5 e minus 3 is probably going to be sufficient in most cases, and if not, print it should have been closer. Okay, so now we still now have to fix the problem in the integration function where we don't have the correct argument, the Q. So that's back in our view controller. So in integration, we now have to add another parameter, the Q, Q-U-E-U-E, and this is going to be type DispatchQueue. Now, this generates another error up here because we're now missing an argument there as well. So we have to deal with that as well. So in here, we don't have a queue. So we need to create a queue for this as well. So to get this to work, we have to go let my queue equal DispatchQueue .init, and we're going to give this one a label as well. And we'll call this one the integration queue. Here we'll have quality of service, again, be user initiated. The attributes here have to be concurrent because we want this to run asynchronously. So the default is a synchronous queue. If you want it to be asynchronous, you have to give it the attribute for concurrent. The rest of this is actually unnecessary, so we can delete that. And then when we call it from here, we have to add the queue and pass it in my queue, the queue we created for this to run it. Okay, that's not bad. So that fixes that problem. Now we have to address in the integration part. So in integration, we now have a new queue in which we want to run things. So now, how do we go about doing this? So we're going to take this let where we created a global queue user initiated and delete that. And we're going to say the queue, we want it to run asynchronous. And now we're going to take the code that we had originally used and put that inside the, spelled it wrong, async. There we go. And then put this inside the list. Now it's going to tell me I have some errors because now I have to let it know who owns some of these functions. And so if I just hit the fix, it adds self to these values, self.dimensions, self.functions for integral. And now this function should actually work. Okay, so now I can actually build and run this code. And see if I get the same results. If I type in 15 iterations, number of guesses, 3,200. May as well do e to the minus x and hit integrate. Now we've got a problem. It blew up. Okay, awesome. So we have a bug somewhere still. And so the question is, where is that bug and how do we find that? Okay, MyQueue, integrations, user, self-integrations, iterations, print done. We come in here, function integrations, the dispatch queue, integral, asynchronous. Okay. Roll around. That looks good. Volume equal that. Fun. Okay. Q.async. Integrations call a service user initiated concurrent asynchronous. Self.dimensions, functions integrated. Integral is not a number. All right, well, let's set a breakpoint there and see what it's giving us. All right, well, we run it through to volume. And there are no values in the integral array. Well, there's a problem. So let's see why that is happening. So guess is that self function for integration. Execute. The joys of real-time programming. Monte Carlo integration. Set a breakpoint there. And let's try it again. All right. Aha! I see the bug now. I've closed the queue too early. There we go. Gotta take that out there. Gotta love bugs. There we go. Now I can kill all my breakpoints because I fixed the bug. Yeah, you always want to get those function closures in the right spot. Controller operators. Where did I set the other breakpoint? There we go. Kill that. All right, there we go. Now we can run this. That is the danger in cutting and pasting. Got to cut and paste the whole thing. Oh, still have a bug somewhere expected. Yep. Still must have it in the wrong spot. Okay. That should be there. Okay. Still missing one. All right, that's fine. There we go. We'll add that. Now we'll rebuild it. All right. 16, 3200, e to the minus x. Integrate. Now we're working again because we have all of this within the synchronous call, which is what it had to have. All right. So I should tab that over a little bit. Probably should tab that one over. Okay. Well, maybe I'll leave it. But now asynchronously in the queue that we pass in runs the dispatch queue, concurrent perform. It fires off each round of the iteration into its own asynchronous queue, does that calculation over and over again. When this finishes within the queue async, or the queue, then it finally, when this finishes, calculates the volume, maps out the integrals, and goes on. This is, again, one of the dangers. It's easy to make mistakes when you're working with concurrency. If you do the things in the wrong order, your function is going to operate in the wrong order, and it is one of the confusing things, and it's easy to make these mistakes. And again, we had to modify this code to make this work for the unit testing. Otherwise, the unit test wouldn't be executed in the right order. And so it's very important to get that right. So if we come back now, we can come back to the unit test. And our unit test, if I test this, is also going to fail for the same reason, because we still don't have everything operating in the right order. But I'm going to test it anyway right now. So I have to stop the running program. We can test it, and it says test failed. And the reason the test is failing is because the assert failed, because 0 is not equal to 2.35. So there are a few things we can see. The integral was actually calculated, although it was calculated, oddly enough, for the wrong one. So what function did I put in there? Helps to go to the right thing. E to the minus x. Oh, that should have been e to the minus x. So exact was apparently off. Why was exact off? E to the minus x. Well, that does look like the integral for e to the minus x. Huh. Well, that's an odd problem. But there are two problems we have to fix, so let's fix the one with the threaded value first. Then we can figure out which one of these it was actually calling, and for the exact value. All right, so the first thing we want to do is go in here, Monte Carlo Integration. Make sure our function's fine. So e to the x, e to the minus x. Okay, that's fine. Okay, integration, tests. Oh, so we have to go back into our view controller. And the reason it's not getting the integral in the right spot is because we're setting self.integral here in its own queue. We're passing that on to the main queue to run asynchronously, and we can't be sure when that's actually going to be called. So I'm going to cut this out, because only things that involve the user interface have to be run on the main queue. And I can pass that in there. So actually, self.exact was not being set, because that's where it's actually printing that out. Interesting. Okay, so now let's see what actually happens. So we must have exact set to, no, that's set to that one too. Okay, interesting. All right, so now we can go ahead and test this. And now we won't have the error with the concurrency. But our testing is failing because now 0.6321 is not equal to 2.35. So how did I screw up that integral? All right. As well just go back. I think that's the same thing that I put in. But we'll copy and paste it from there just in case. There we go. So I must have typed that in wrong somehow. Not sure how I typed that in wrong, but now our tests are passing. Sure what we did, but if we scroll back up into here, we will see 0.6328 is equivalent to 0.63212 within our error bounds. Okay, so now we have a functioning program with at least one functioning unit test, but we want to test all of these functions. So we'll just copy this. Then we'll make this integration of e to the x. Here we have our function e to the x test. Let's see if I can not screw this one up. So that should be e to the 1 minus e to the 0. And it should be roughly in the same number of iterations. So we can test this again, product test. And now what did I do wrong? Oh, 0.63. Oh, lovely. This is not e to the minus x anymore. This needs to be e to the x. There we go. Kill that. Kill that. Now we can test that and it should work. Yeah, don't try live programming. I'm a trained professional. So now we've passed this test. We have one more test that we want to include. And that's going to be the test of our 10D integral. So this will be 10D integral test. Now, our dimensions here, before I forget to screw that up, that has to be 10, and I never remember what this value is, like 255 over 6 or something, so I'm just going to go back into where we define this and set the exact value before. Oh, that was a view controller down here. There we go. It is, 155 over 6. run this test now. And now it passes all the tests. So we now know that everything is functioning and everything functions. And that's good. That's a very good start. But we did have to make changes, and we saw that you have to be very careful with the concurrency, what gets returned when, and how you have to change things in your code in order to make sure. So we did have to make some changes to the main body of our code in order to allow the unit tests to work. And so that was very important. And we had to do it in multiple places in the code. Now, if we want, we can set a breakpoint here, and we can go ahead and run the code. "15 iterations, 3,200 guesses, and well, let's just run e to the minus x, hit integrate." Now, when we stop here and go into the debugger, I can slide this over, and we can see what queue we're actually in. We can see we're in the integration queue that we named it, and we're running this concurrently. So that's a very good thing. We can now see a little bit more information if we need to see where we're actually at within the code. Now, if I want, I can move this breakpoint down inside the next concurrentPerform, where we farm off to multiple threads, and I can hit continue. And so now we see we're within a user-initiated quality of service concurrent queue. So it tells us that we're actually in something that was user-initiated, so it has very high priority, and it's operating concurrently, and you can see a lot of the different threads that we have now actually created and are running in. And so we can see each one are doing Monte Carlo integration here, thread 12, 13, again, concurrentPerform iterations, Monte Carlo integration. So we can see a tremendous amount of information by using the debugger to find these things. All right, so now I can remove this breakpoint, hit continue, and we eventually get our answer. So now that we have a lot of useful information, code that works, we have testing that we would see if we destroy the code accidentally in some way. All this is very good, but we don't necessarily know how the code is operating. And so we can actually do a little bit more to get information on how the code operates. And so let's add that in as well. So let me stop this. So I'm going to add a few new variables, and I'm going to import one more thing. So I'm going to add logging. So I'm going to add OS log into the code. This will allow me to send information to the computer's logging capability, and that way I will always have access to some of that bit of information. So I have to let log equal OS log. And I have to give it a subsystem and a category. And so the subsystem will be bundle.main.bundle identifier. And I'm going to have to tell it, even though it's an optional, that we know it's there by adding the exclamation point. And the category I'm going to say is information JT. Okay, so now I have a log, and some of the things that I want to actually log in here will be how long it takes me to operate. So I'm going to have a starting time that will initialize as a dispatch time. And we'll just take the value as now. I'll have a stopping time. That will be a dispatch time. And we'll also initialize it to now. And this will hold the start time. This will hold the stopping time. And from that, we'll be able to figure out how long it takes us to actually do these calculations. Now we need another variable, nanotime, which is a uint 64, and this will hold the time in nanoseconds. We'll initialize that to 0. And we'll need a time interval, so we can figure out how long the thing took. This will be a double, and we'll initialize that to 0. Okay. So when we start the integral, we're going to want to set some of these parameters. And we'll use these to actually figure out how long it took us to go. So we'll have start equals dispatch time dot now, and this will give us the starting time of the integration. And then when we return down here, we'll actually want to stop it. So we could perform this on the main thread, or we could perform it afterwards. If we were going to display it on the within the GUI, it would make sense to have it in the main queue. So we'll put it here just to make it easier. So we're going to have stop end equals dispatch time now, and this will be the end time. Now there's a problem because we've put it here and it doesn't know what the identifier is, and so we have to go self.end. And did I call it? Oh, I called it stop. Okay. So stop. There we go. Self.stop. So we have start and stop. Lovely. Okay. All right. And so then we're going to have self.nanotime equals self.end, self.stop dot uptime nanoseconds minus self.start dot uptime nanoseconds. And so this is going to give me the difference in nanoseconds from the start of the calculation until the end. And I'll go self.time interval equals double self.nanotime. And then to convert to seconds, we have to divide by the number of nanoseconds in a second. And so that's going to be 1 billion. All right, so one of the things about Swift is Swift has the ability to use underscores to help break up numbers. So I didn't have to put in the underscores here, but according to the Swift guidelines for usability and readability, you should actually put that in. So we'll put it in there, self-time interval. Now I'm going to print the time to evaluate was self.time interval and that's in seconds. Now, print just displays down here in the console. But for logging purposes, you want to use OS log. And we're going to do time to evaluate was, and unfortunately we can't use the shortcut notation like self.nanotime. I wish that actually worked, but we have to use the old C-style format strings. And so we're going to go 5.5f, and to give it some decimal points in seconds, period. And then we have to do log. So we have to tell it what log to go in, and that's self.log that we created above. And then what we want to print in the string, and that's self.time interval. Now we should end up with something that gives us the time it takes for each calculation and actually puts it in the log. So let's build and run the code now. And ideally it will work. Number of iterations, 15, 3200, e to the minus x integrate. And now we see here the time to evaluate was 0.05797 seconds. So that's pretty good for us to get 0.6335, 0.6321. If we increase the number of guesses by an order of magnitude, the time should also greatly increase. And so it goes up to 0.48615 seconds. Go up one more order of magnitude, integrate. And now we're up to 4.7 seconds. But again, even though it took 4.7 seconds, we didn't get the spinning rainbow cursor of death because we've run this asynchronously. And so we don't block the main thread while doing it, so we've greatly increased the operation of our code. So that's a very good thing. And now, if we want to make sure that we're running in the log, we can come down here, and in other, we can launch the console, and the console stores information about the log. So if I want here, I can actually search now for the word seconds. There's so many things flying through here. And nothing says seconds. Awesome. Why does nothing say seconds? Should be in there. What's the log? Let's try category information JT. And nothing. Lovely. So the log is not working properly. Cool. All right, so let's see where we screwed up the log, because the log is actually a very useful thing. This log time to evaluate. Self.log, self.time interval. Bundle main identifier. That seems reasonable. Imported os.log. Okay. JT. Yeah, that should be correct too. Ah, there we go. There it is. All right, I have no idea why it didn't work the first time, but it worked the second time. Oh, I hate when things don't work, and then you have to, no idea what the difference was. So maybe I didn't rebuild the code, don't know, but let's quit it, run it again. Every now and then, things that should work don't work. No idea exactly why. Okay, 0.05 seconds, console. Just may not have updated. Seconds. And there's our process integration. Time to evaluate was 0.0534 seconds. So that's our last one. The one before that. Yeah, so maybe I didn't rebuild it. Don't know what it was, but yeah, it was all in there. Works fine. And so these logs are stored, and you can see the category is information JT. So I could have searched for it with that, or I could have searched for it with the subsystem, my integration threaded program, and I can get the activity ID, the thread ID, the process ID, all this information that's stored now in the log every time I call this logging operation. So if you need to save something that might help a user to figure out why their errors, use the OS logging. It usually works. Again, I have no idea what happened the first time, but it's a very useful thing. So now we have code that passes unit tests, and we should actually check the unit tests because we have made some changes. So we can come down here, test it again. Oh, test failed. Oh, lovely. So the question is, where did we fail? And this is one of the problems with unit testing, and it wasn't within the desired accuracy. So 1.72 and 1.72 to us is the same thing, but is not within the computer to 0.05. So if I really want to minimize the risk of that happening, I could either change the accuracy or I could actually run the calculation for longer. So I may as well just increase the number of guesses each time. And let's try unit testing one more time. This will take longer though. But I don't unit test every minute. Oh, I still failed. All right, failed on the 10D integral. And the reason I failed on the 10D integral is because even with this number of guesses, it's still not that good. 25.81, 25.83. So I should really make this change the accuracy or increase the number of guesses. But this should be good enough for testing. So now we'll change that, run it one more time. And we've passed all the tests. So again, there's always some challenges when you're doing testing with numerical accuracy. You have to use reasonable values of accuracy for the length of your test, and this is one of the issues with Monte Carlo integration. It takes a long number of guesses to converge because it is roughly goes as 1 over the square root of n instead of n. So it takes a long time. So you need a lot of guesses to get good results. But you can get results on very high dimensionality. And so that makes it a very useful thing. So let's test it one more time, make sure they all pass. And their test succeeded again. Perfect, so we're good enough. This is good. So we now have a program that is still limited in one regard. And the one thing it is not doing very well is it still does not do any integral except for the region from 0 to 1. That's a major limitation, and that's the limitation that we'll address the next time. But right now we have code that will calculate Monte Carlo integration over multiple dimensions for at least 3 functions. It's easy to extend to other functions. We have written unit tests that work concurrently, and we've added logging to the code so we can actually look up later on how long it took to actually run each calculation. And this is useful information to save. So we've done a lot so far. We're still missing one thing, and we'll get that done for the next time, and that is to go and allow us to change the limits of the integration in all the dimensions that we add in. So that'll be the next step, and with that, talk to you next time.